Hello guys, welcome. So today we are going to be implementing GANs. Before going into the code, let's look at the plan of actions and what we are going to go do and where do we start these things, all these things. So let's let's start. Let's start it. So first of all, let's discuss about plan of action. So plan of action today. So first of all, what we're gonna do is just first of all we will download download data from Kaggle. So from Kaggle we're gonna download data from Kaggle, and after that we will move on the move on down. After that we will visualize some data visualization. So before visualization we will do one thing. This is third, and before visualization we will first of all first of all we will just store data store the data data into the RAM. So store the data into not in arrays, in numpy array. So numpy array. So we will gonna store the data in numpy array. After that, after visualization, and after that we will move on to the next thing, which is after we will do visualization, then we will go on model creation, discriminator model creation, discriminator creation is a discriminator model. So we will develop discriminator model, which is a CNN classifier. After that we will look at on, and we'll just create some utility function. So like load images, we'll create some utility function to load image, load and create fake sample. So we will create this function. So to load and to create the samples, so we will create some utility function. So I will write utility function, so utility f, and after that we will, after creating some utility function, we will test our discriminator test our discriminator from random to the random data which is not created by the generator actually. So we will test our discriminator just for our understanding. So and we will not use the generator to generate samples. So we will use our we will use our function. So with function we will create our own function. So that will create a random image, that will create some random images. So that will create random images. So we will use that to train our discriminator and test our discriminator. And after testing that this is not a real actual discriminator training, but for our understanding of discriminator we will use we'll use this. So after that we will go on the model creation of the generator. So for generator, so we will what we'll do, generator we will focus on, we will we will focus on creating creating a image generator which will generate our images using CNN, creating a model with con 2D transposition. What we'll do, we'll 2D transposition in which convolution we'll using, this type of convolution we'll using, and we will create a generator. After generator creation after generation creation we will focus on another part. So after the generator we will focus on training defining the composite model. So defining the composite model. After that we will define the whole model, so whole or composite model. So we'll focus on creating whole model. So after that we will focus on After that we will go on if we define whole model, and we will do main training will happen after that, after the creation of the discriminator. So after that we will focus on main training. So we will train both the discriminator and generators in generator. This is just for our testing purpose. Here this training is not real training, but for our test we will train our discriminator to see the to see our to see the capability of the discriminator to fake images. So it's not a real training. Actual real training is here. What we're gonna do, and after that um, we will focus on maintaining, and then we will after training we will summarize performances of our model. So we will summarize performances and we need some utility functions here. Utility function means we will create some functions, and that will help to create help to create to our models, which will help to summarize our performances. So we'll creating this model, and after that we will see some prediction of images on our we will do prediction. After that we will do prediction. So prediction is going to happen after creation of this. So prediction is needed. So uh, prediction or generation, we can not say, but generation is better. So after that we will focus on generation. So and this is our approach. Let's move into the code, and I will use this for further explanation. So let's move into our code. So so this is so this is our code. So let's move into it. So what we are doing here is just downloading some importing some libraries, numpy, pandas, and OS. So after that this part from here we are just downloading from here to here. We are just downloading data directly from Kaggle to our Google Colab. So and you need to upload here from here Kaggle.json. You need to upload here from from here. You need to upload kaggle.json. If you have not downloaded, just downloaded this file kaggle.json. So you can just upload here, and so you can upload here. So and this is needed for our for this downloading data directly from Kaggle to Google Colab. So we need Kaggle.json. So you must download it, and this is our NumPy. This is we just importing some basic libraries, NumPy, pandas, and OS. After that, this code is from here to here. We are just downloading from here to here. What we are doing first of all, we are making directories, and you have to command. You just run this command, install pip install Kaggle. So and after that you need to run this command. So after that you need to download this and just write this we will gonna using this dataset. So just just paste it and just run it, and your data will download it directly here. And after that you need to create some directories. So I have just write as make dir. After that you have to unzip the data into this directory in train. So the data which has been downloaded, this will be get stored into this train. So after that what we are doing here, just this will be so let's run it and you will see it. So if we run it, it will download the data from Kaggle to. So if I run it, so it will download the data directly from Kaggle, and it will store here and make a directly train. So it will unzip it. So and after that we have to there is some there it will create this directory here into here. So we have just I'm copying the path of the image directory where the images will be stored. So it will store in this directory. So I am just writing image directory and importing Python imaging library image, and this is the image shape. We are gonna using 64 by 64 images. After that, what I am doing here is it's just creating one list, and this function actually just store the data into this array. It will just create some numpy array, and we want to store into this array, this single array. We want to store all the images into this array, and we want to split it into extend and test and train. So we will need this. So what we are doing here, just going to the, it is unzipping it right now. So it will take time. So if you have there will some one untrained directory in that train we have to and we are in the train, we there is this train. So here, what are doing here, what are going here, actually there are images. So if I can see it, but it's not showing. So in this directory we have images. We have nearly 2000, nearly 2 lakh images. So we will not use this whole images, but we will only use 50,000 images. So I'm just, we are just using, there are many images files. So we are going through the all the list, running this os.list dir into this image directory. So and we will go up to 50,000. So if I is less than 50,000, so if I is less than 50,000, f path is equal to, we're just joining this image directory path, and the each content, each file of this directory. Inside this directory there are some images, like some, like I will show here. And so here is this images. So this is just jpg, just this is a directory. So this is the images, and this is a directory which has been stored in this in this folders. And so uh, and we are just appending this and just joining this and this. So this part and this part. So what you're doing here is just joining this and just opening it, this file path, and resizing it and appending it. This resize image shape means 64 to 64. And after that, and I will, why we are define this constant. So I will, this condition I will tell you. So after that, if this all the images will be stored in this, all the images will be stored in this list, and we will convert this images into numpy array. So we create another list here, and after that we will do x in range of this length. So we will run this. So what will it do? It will run this loop this many times, and we are converting each into numpy array of this data type. So and we are appending it into this list, another list. And after that, we can convert this list into a numpy array. So our whole our whole images will be converted into numpy array, and this list will become numpy array. So for that we will get some array of this dimension. So this means 70,000 images of size this, 70,000 images of size this. So this is our size, and this is our shape. So and what I have done here is just defining this int here. So and I am just, because I don't have a GPU, so I can't just train nearly 2 lakh images in this directory. So I'm just accessing 50,000 of it. And if my images is, I'm just up to less than 50, less than 50,000. So I'm just storing this images into my this list. So after that, I'm converting it. And what I'm doing here is just importing the matplotlib, and I'm just showing the images what is shipped in this numpy array. So I am just showing this. I'm just going to the 49 times. So I'm creating the subplots, and offing of the axes, and I'm just not showing axes, and just I'm showing this using I am so method, and so I am just showing the 49 images. After that, what I'm doing, uh, if I have and so I am just writing this pyplot.show. So after this method, as in you will see this images. So this is the images which is present in the this data set is this is the picture of celebrity. So and it will if I just go through the up to 49, so it will show the 49 images of the celebrities. So I'm just showing it for our visualization purpose, and this is shape what is already written so on it. So and this is 64, which is not very low, but 64. So this is just using 64 dimension, but uh, you can just do 32 also, but the 64 is better. So I'm using the shape of 34, and after that uh, we will go on model creation. So model creation model creation, actually we will first of all create the discriminator, and then after we will create the generator. So for model creation, what I have done here is just importing some libraries. So libraries, not layers. I'm just importing some models and optimizer layers, which is present in keras, and importing sequential atom dense, and this is used for the a discriminator, and this is used for the con 2D transpose. So this mainly used in downsampling, and this is mainly using this is mainly using upsampling. So this is usually, so it is using discriminator, and this is using generator. And after that I am just using flatten dropouts. I think you know it, what flatten does. And so dropouts and the Lekki Relu, and just receive this. I think you may not know this receive. So this will just convert the one dimensional into if we have some one dimension, just receive it, not one dimension, but in our cases we will just convert the one dimensional, say, length vector into just a two-dimensional grid or two-dimensional matrix. So we'll convert use this receive. So and this plot method is into plot our model, and importing numpy, I think I have already imported. So let it and there is some empirically this leaky relos work better in case of GANs. So there is, and the scientists has found liquid relos in case work better. So after that we will define the discriminator. So for discriminator, we are just taking the shape of this dimension 64 comma 64 comma 3, and we are initiating this sequential model here. And what we are doing is just taking this shape and just using what to con 2D with 64 filters and the corner size of this, and making padding as same, and giving this input shape to this first convolution layer of our model. So after that we will apply Kirelu, and after that we will apply another convolution with 128 filters with size same as any, and we are going to be using strides. Strides have been work better than max pooling in case of GANs. So we are going to go with strides then the max pooling. So after that we will apply another consequently another with con2D and value of with also value of zero point 0.2. And after that we will do some flattening operation, and after that we will apply dropouts, and after that we will, this is a binary classifier as we know. Since so at the output we're gonna go outputting value between 0 and 1 using the sigmoid. So we're gonna be using sigmoid activation functions, and it will give the value between 0 and 1, and for real it will give the value closer to 1, and for the fake it will give value closer to 0. And after that I am defining the optimizer for the discriminator, which is Adam listening with learning rate, and the beta parameters beta 1 with 0.5. So and after that I am compiling the model using cross entropy binary cross entropy loss, and I'm just matrix giving as accuracy and optimizer as opt. So and returning this function, when I call this function, it will return this model. And what I'm doing is just defining the model here, and just printing the just doing this just seeing the summary of the model. And you can just also plot this in using this utils and garage.utils. So just you can just plot the model and see the model, and it can also save this model to this file path. So I have to import I have to run this because my I lost the connection, so no internet access. So I will run it. I will after that is an it has I have already run, so you can just see the results here. So it's not needed actually, so I have already run it, so you can see the results. So this is the summary of the model. So it has the model sequential, and this is look at here. So uh, here we have layers names and output shape. So it has parameters of this and this. After that we're just going into it, and we have nearly a 5 lakhs parameters, so which is which you can see here. So and this is our layer, this is a plot, isn't it? So it will take this input shape, give output this input and output this. So I think it has been bigger, so let's make it small. So likirelu, it does not change the shape. And after that take this shape and do this. And it consequently is our image will be reduction. This is just the dimension of the image as is reducing, isn't it? In flatten, isn't it? From this array is in this tensor, isn't it? We converting into one dimensional tensor. So this is, we can see here, this is just the vector, isn't it? So not one dimensional, but this is a vector, isn't it? So vector is 1D vector. So this is just 1D vector. So and after that, this is our shape, and this is our dense. This are dense, and this will give one value which is sigmoid, isn't it? And I'm creating some utility functions here, so which will load the real samples from this 10x, which is a numpy array, and it will, and I'm using the type as float 42, and I'm just doing normalization of images to standardizing the real data and just returning this. And I want to tell you any one thing. So we'll not gonna go up. We will not gonna give those any all the images to the discriminator at once, and update the weight at once. So we will not gonna go do that. Isn't So for the discriminator, we will give it into batches, in batches of 20. We are going to be using a batch of 120 images at a time. So we will give 120 images at a time, and we'll update the weight on these images, so on 120 images, and next batch, and it will again update its weight, thus getting better at each step. So you have to understand that we're not going to give this at once. So and update the weight at once. So cons- we will we'll update the weight as in each batches, and so and this is we will and we're not upgrade at once. And after that, and I have created I, I I have created this two methods in which will generate real samples and fake samples. So this will just take this data set as a data set, this two parameter data set and n samples, and after that do it will do just we are just using random to get some samples. So it will what to would just sampling random sampling. So we are giving this 0 and the data shape dot zero, so data shape dot zero, and number of samples we need. So and it will, and we are what we are doing here, we are just we are giving this random machine. So we are just selecting random data and just selecting some random data, this many number of samples. We are just selecting the random, not data, but just random numbers, and we will using this random number, we will gonna go sample the data from the real data set. So not sample, but we will just randomly listen. So randomly just select some images from the data set, and I'm creating this numpy at once. So which has um, this is the shape of the number of images. So we'll create the one dimensional vectors. We'll create one dimensional vector of all ones, and how many images we have. So if we have nearly 20 images, so this vector will be the length of 20 elements with all elements 1. So this is our just number of images. After that, and it will just be the number of this is just be the this is our x and y, so for the real samples, and we're just returning this, isn't it? So X will have one batches of images. So I think we gonna go take this 64 from the real and 64 from the fake. So at one time. So after that, Y store one. So to add identity to identify all the images that come from the real data set. So and after that we will create another method in def generate fake samples. So what actually do is just we are doing just running the rand. So and it will sample, it will just take sample from it, and this is just numbers 64 comma 64 comma 3, and this is and sample how many sample we need. So we're just sampling this many numbers, and we are gonna just doing some normalization, putting the values between -1 and 1. So it is just this operations what we're doing is actually just making the values within the range between 1 and minus 1, which will necessary for the for no, which is necessary for our model. So and after that what I'm doing here is just creating this patches, isn't it? So what is it will contain, it will be a number of samples. After of course we will gonna go take 64 samples, isn't it, from the from fake images. So and 64 we will images we will gonna go take. So it will be 128. So we will, this is just dimension, so I'm not, don't be confused, in this is dimension is in of images, and this is and sample is number of images. So and we gonna go create the same length vector as in one single dimensional vector which contains all of zeros is to identify this is the fake samples, and which has been generated by this function. So we will, after that we will create the generator, not use this functions, not use this function to generate samples. So for our testing of discriminator, we will use this function for right now, and after that we will create our own not discriminator but generator to generate samples. So for now, for testing our discriminator, I am just creating this function, so which is just it will just noise random noises, and so it is just taking some random number from the this distribution random dot rand. After that, just not just bounding the values between -1 and 1 and reshaping it. This is we are just making the batches, and it will return us in 0 will indicate the fake images. And what we're doing here is just see is just creating this generate fake samples. So generate fake samples, giving the number of samples, and it will just I'm just showing here. This is the first zeroth zeroth element. So just showing the zeroth element. So you can see this is the image created by this function, so we are defining this method def train discriminator, which will take model, this is the parameter of the function. So we give this model data sets and number of iteration and number of patches. So and we are just defining half patch, so which will a number of batch by 2 is number of batch by 2, and a half real and half fake images in one batches of 128 pixels. So and we are just generating the real images and training the models in discriminator model on batches. So we will not gonna go train the model at once, so we're gonna go train the model in batches, several batches, first we will train on one batch, after that one batch. So model will not gonna go train the discriminator at at once. So we're gonna use this method as any train on batch, and we'll update the discriminator weight on fake data, and similarly we'll update the real. What we're doing actually here is just we are just going from 20 times. So we are just going 20 times and generating the this data set, this data as an x real and y real, and updating the data on real data, updating the discriminator weight on real data, on real data, on real data, and just training the models in this generated data as an for the on the one batch. So after that we will generate fake samples. So and we will gonna go train on batch. So after that what I'm going here is just defining the model discriminator, defining the discriminator, and loading the real samples. So load real samples, and after that what I'm doing is just calling this function train discriminator and passing the model and the data set is in this method will load the data. This load is in data, so I'm just passing it here and just training the model as in at starting as in the accuracy is this. I think if you just once you train it as in it'll converge this. Actually, it's converged into 100 and 100%. So if you run it as in it will converge this. So for the real, what this matrix actually telling is in our mode, our discriminator is 80 85 87% is in distinguishing this is the real, and 40% is distinguishing as fake. So 44% is this accuracy, and so we are just printing accuracy. Just see the 40, there is accuracy of 44% is in the fake, distinguishing fake, and real is 87%. After that, it will converge into 100%, isn't it? I think we have to retain it. So, as in it, but in my times, it has conversion in the previous time. So, anyway, just run it and it will converge, isn't it? So, after that, and because this is just why this model is easily get converged, because this fake, this is getting 90% accuracy, 90%, because this is it can easily distinguish in real. Fake images look like this and real images look like this, is in what I have shown earlier. So it can be easily distinguished. So for the discriminator, it's not a hard task, isn't it? This and this, it can easily distinguish, and model discriminator model will surely converge, isn't it? So this is the discriminator model, and after that, just importing this reshape layers and the 2D transpose layer, and let's guys move into the creation of the generator neural network. So and the input of the generator is random noise generated from the Gaussian distribution. This is just a random noise, isn't it? The input for the generator is just a random noise, just a vector, isn't it? It's just a vector, isn't it? So I will show, isn't it? So this vector, isn't it? So if I can show, so look at here, isn't it? So this is the vector. So this is just a 100 dimensional vectors, and so this will contain the values like this up to here is an x 100 is an n is 100 here, and this is a 100 dimension. So n is 100 here. So after that you can see here, and this is the 100 dimensional vectors, and this is a 100 dimensional vectors, and this value is just sampled from this value will contain the value from the Gaussian distributions in a Gaussian distribution. So Gaussian or normal distribution, you can see. So this is our z, isn't it? So z is equal to this value. So this is our z. So after that, let's move on to it. Isn't it? So the input is just a 100 dimensional noise vector, isn't it? And this noise in terminal in literature called a Latin variable. So and output is not actually 32 or 42, but this 64 plus 64, you can just change it here. So just I will change it. So to 64, 64, 64 into 64 into 3. And this is the output, isn't it? 3 specify the RGBs in. So let's go on to the model creation, isn't it? So 2D is used to upscale. 2D is not used to upscale. 2D is used to downscale the images. So 2D is on 2D transpose is an boundary transpose is used to upscale image picture. Upscale means just from 8 to 8 cross 8 image to 16 cross 16. So to upscale we use con 2D transpose, and to downscale we use con 2D SNE. And Latin dimension is Latin dim is noise. So just dimension of the Latin noise vector. So noise dimension of the noise vector. So noise vector. And our generator want to understand and graph the distribution of the data in our real data set, and so uh, so as to generate such an image as any, we start from the small image as any 4 cross pro, and then upscale to 64 cross 64. So 64 cross 64, 64 cross 64. So we'll start as in, we'll start from the 4 cross pro as in, and then we'll move on as in. So just I am just calling just define, and I'm again creating the method as in function. So which will take those in Latin dimension, and I'm again creating the sequential model, and it has this is an I'm creating the first nodes, and this will be contain dense dense with this number of nodes, and after that what I'm doing here actually is it's just after this first neural network I'm just applying the Kirelu. Number of nodes is this isn't it? So and using alpha is equal to this and reshaping it to the shape of this, receiving to why I'm just actually why I'm taking this. So as I mentioned why I'm just doing this, so why I've just specify this number. So as I want to start from 4 cross 4 with this many dimensions. So this is the just channels isn't it, this many channels. So receiving into this and so after that I'm just receiving this is just let's go into the picture. So I will show with my pen. So let's go down. So let's see our generator network. So I will gonna build it from scratch. So it will just what will give is just this. So this is the order dimensional vectors which will contain these values in 2 up to xn, which is n is equal to 100, and also will pass through the neural network which contains the first neural network. And after that, guys, what we're gonna go do is we're gonna use some receive layers in receive layer. This is the receive layer. So this is the receive layer. So it will receive into the two-dimensional this connection is, you can just connect all these arrows. So as you can just connect this all these arrows. So you can connect this. So and it will go through the first convolution. After that, it will convert into a two-dimensional vectors and two-dimensional shape, and we'll convert from this shape to this shape and to this shape. So we are moving from this shape to this shape. So so this shape to this shape we are going from. So we are going from this shape to this shape, and after that we will gonna go pass it to the convolution layer. So we will gonna go pass it through the convolution layer. So I'm learning this pen tab. I have not used it, so I'm learning it. So this is CNN, this is CNN. So after that we will gonna go pass consequently the more CNN. So CNN we will gonna go use more CNN. After that, this is the architecture of generator. So and this is transpose, and in this we will gonna be using this con 2D transposes in transpose. So this is a just over. Just I just want to give you this flavor. So and what we are doing actually in generator part is just first of all just passing this Latin dimension, this 100 dimensional vector into this first layer of first dense layer and applying Liquid Lewis and reshaping it to the 2D scene. And here the stride will upscale the image double of its size from this 4 cross 4 to 8 cross 8. So when you apply this convoluted transpose is with this many channel, this many filters, and this many. This is the kernel size and strides. So and it will transform the image from the 4 cross 4 into the 16 cross 16, as not 16 cross 16 but 4 cross 4 into 8 cross 8. So this is just we are doubling it, isn't doubling it. So and so to will upscale the double of its size, so double of its size. So and if you again apply this convoluted transpose, it will convert into 16 cross 16. And if we again apply it, it will become 32 cross 32. And if we again apply it, it will become 64 cross 64, isn't it? And after that we will just apply simple convolution, isn't it? 2D is not where not using, isn't it? Convoluted transpose here, isn't it? And it will just we are not using so many filters because we need just three channels, so we are using just three filters. And I'm using tan s is equal to, isn't it? Tan s is equal to, isn't it? Activation and tennis is equal to this, isn't it? So and padding is equal to same. So why you're using activation tennis? I think you can just relate to it. We have just bounding the values, isn't it? The domain is the domain of the not domain but the output of the tennis is between minus one and one, I think. So and we are also using the also using this we do minus one plus. So you can remember it, isn't it? So here so yes, we are just making the values between the write a comment, isn't it? Making the values, isn't it? Making the values in between, isn't it? Between one and between this I want to write it, isn't it? Between minus one and one. So this is the close form. So after that, I'm closing it, and after that, I'm just defining the Latin dimensions, and this will define models in a model define generator, and I'm defining it, isn't it? So define generator, I'm just defining this generator, just giving this parameters and Latin dimension and just seeing the summary and plot. So let's see the summary and plot of the models. This is sequential too, isn't it? So after that, what you're doing, you're just using this dense as above mentioned. So parameters, 1 million parameters we have, is nearly 1.7 million parameter, and this is the plot, isn't it? And you can also, if you run it as in sales, this will store yes. So, and let's see, it will take this 100 dimensional vector, convert it into this in a many, will pass through the dense layer. So we get this many values from the each node, this many nodes, we will get some values in it, and it will pass to this Likirilu and reshape, which will convert into the shape of this dimension, and after that, we will gonna use quantity transpose, which will just upscale by two, isn't it? Just factor by two, this size, isn't it? Height and width, isn't it? So it will just convert it into two times two, double it, liquid doesn't double it, so transpose again double it. So we'll get this shape, isn't it? So we'll get this shape last layer, so we'll get this shape of and not 128, just three channels. At the end, isn't it? We will get what size we'll get 64 cross 64 cross 64 cross 64 is in cross 3 is in 3. We'll get the same size. And after that, now we have to now we have to build both and join them. So we have already built this is any generate and discriminate, and we will need to join them in order and make them feedback and send make them to send feedback. So it will feed is in one it will feed 128 images to the to and it will feed 128 images assumed at at a time, and 64 is comes from the real dataset. So we'll feed 128 images, and 64 will come from the real, and 64 will come from the generator. So generator, and what we are going to do here is just merging the generator and discriminator as adversaries. So So what we're just writing this as a name. We're just merging generator and discriminator as an adversary. We will see the plots also. See also the how this merging happen. So and I'm just creating some this method which will just create Latin points. Latin point means just this say vectors in. So what will it take? It will take some. It will take x input and we're gonna receive it into the number of samples into Latin dimension. So it will send the 164. It will give 64 100 dimension noise vector, or it will just give 64. Yes, 64 100 noise vector noise or image to the generator, and it will give us 64 64 cross 64 cross 3 so dimension images. And we again creating some another methods so uh which will take these Latin pointers. Latin point means 100 dimensions. This will just give 100 dimensional vectors. So we'll pass this as any 100 dimensional vectors into this generator model in which we have defined here. In this generator model will pass to this images, and this generate Latin point will pass to the generators model, and we will do because this is a fake so we have to give the label as zeros zeros. Np dot zero means it will create some length vectors one dimensional n-dimensional vector all values having 0 0 0 0. So and we are returning it, and we just want to see how our generator is generating at this point. So let's see how our generator model at beginning we haven't trained it. So we want to see it how it's performing. So let's see how this model is actually doing. So we haven't trained it. So we just giving the Latin dimension as 100, defining this generator model and passing this Latin dimension. The number of sample we need 49. So just I'm passing it in this method. In this method, what will it take? It will take this model model means this generator model, and Latin dimension means 100 dimensional vectors. We just define the shape and number of samples. How many samples we need? We need 49 samples. And what I'm doing here is, and we doesn't need y's right now because we're just showing it how the our generator is just doing some y or generator is predicting the predicting the doing this job. And so I've run it, so it is not showing. I've just recently run it, so its output will not be shown. So model is saying so model. I just I'm defining it and sample 49, and it will generate some fake samples and just doing normalizations. And just I'm plotting, I'm creating subplots with this shape, with this shape and axis offing, and just showing the 49 images here. So I have recently just clicked it, so it is not showing the images, but it will just print 49 49 this images, this type of images, but all are gray right now. They all will be gray right now. They all will be gray. So we will create this 49 gits, and all will be gray. All will be grays. So I will give it when I run it. So all will be gray. So I have just run it, so it will not showing it. So I click it, so it doesn't happen. I will run this code and I will train this model train the model, and I will send you this notebook. So send just give the link in the description. So and let's merge now. Right, let's merge the generator and discriminator and train them simultaneously. So let's understand it. So go into the notebook. So go into the notebook and just understand this is what is this composite model. How we will gonna go now. This is the main training, guys. We have already trained that the discriminator. This is not a real training. This is just we want to test the discriminators. The real training start here. So we- so we'll see it, isn't it? We will gonna go defining this composite model, isn't it? So let's move on and see. So let's wait and see it. So this is our actually working. So it is outset. So you see it, isn't it? And this is our generator G. Some samples to generate some samples. So fake samples, isn't it? Fake samples. So fake samples, fake samples. So it will generate some fake samples. So we'll generate some fake samples, and this is our real data. You consider that this is our real database. Is real database. This is our database. So database is our data set, isn't it? Data set or database. So data set. This is our data set. So data set, you can just write it. So if we're gonna go passing this and this discriminator. So discriminator, isn't it? Which main job is to classify which image is real and fake. It will say find some loss here. Isn't it? This is a loss, isn't it? So loss. This is a loss, isn't it? And we will from this we will what we will gonna go train. We will gonna go train this both this generator and the output. We will gonna go train generator and this discriminator itself. So this is a composite model, isn't it? This is the composite model. So this is a whole this model is a composite model. So first of all, we will train the discriminators and discriminators. When training discriminator, we will take the fake sample, this fake sample and real data set. So while training discriminator, we will generate data. So we will generate data and generate some fake samples and take we'll take 64. So 64 discriminator and discriminator will and we'll train the discriminator. So discriminator will be trained. So we'll and there is some and when while training the discriminator we will not gonna go train the generator. So generator while training discriminator I will just write in while training training discriminator while training discriminator we will train generator. So this point is should be very carefully understand. So while training discriminator we will not gonna go train. Let's go into the discriminator training first. So in 120 images we just sample we just take 60 and 64 from fake and in one batch. So in one batch so we will discriminator discriminator on multiple batches and the generator in multiple batches. So we're not gonna go train we'll images at once and train the make the discriminator capable of distinguishing real and fake. So we're not gonna go do that, isn't it? So discriminator at once. So we will first of all train the discriminator in 128 images. After the discriminator training, after this training is happen, isn't it? On one training, when happen this training will happen, isn't it? We will we will work on the generator training. So first so train this on this 64 image on this 128 images and we will do and discriminator will learn the real and fake. So real and fake. So and first of all, how the training actually goes of discriminator. So we'll pass this level, this level as 0 and this level as 1. Give the this is level. This is a level 1 and the discriminator will do predict the real and fake and there is some loss. It will back propagate. It will only discriminator. This loss will back propagate the discriminator only. So we'll back propagate the weight back propagate the errors in only. We will not gonna go we will not gonna go any, not gonna go any backward bracket this backward bracket it's, so we'll not gonna backward bracket to the generator. So we'll backward bracket to the discriminator and update the word of discriminator become capable, isn't it? Capable. So discriminator become, so discriminator become capable. So capable of, capable of, capable. So capable of distinguishing real and fake, isn't it? Real and fake. So if we train in 120 images, it become little bit of capable. So not at most as capable, but it will become little bit of capable. And after the after the training of the after the discriminator training is in 120 image, we will redraw it to for, and this is our data set. So this is a real data set, and so it will generate fake samples. Fake samples. This is the fake sample, and this is a discriminator. It will go through it, and this is a fake sample, fake data. So and there is some backpropagation here happening, backpropagation happening here. So backpropagation, backpropagation. So there is backprop happening actually, backprop. So how it actually look like? So first of all, generator will generate 64 fake samples, and we will pass. I think I am. It could be 64 and it could be 120, isn't it? Because I have to see it. We will not gonna use this, isn't it? This right now. So we will not gonna use the dataset while training discriminator. We will not gonna use real dataset. So in real dataset will not be used while training. Will not be used in while training the generator. So we will not give the data to the discriminator. We will just generate fake data and pass the discriminator, and this loss will not propagate to the discriminator while training the generator. So this loss will be propagated to the, we will generate fake data, some fake data, and nearly this data, this 128, and we'll pass to the discriminator, and the discriminator will classify using, and there is some loss, and we will back propagate that errors and make the generator. And there here is some tricky things I want to tell you. Since so here the fake data, we are giving this fake data to the discriminator, and discriminator will, if you give this fake data to the discriminator will easily distinguish this as a fake, and so it will easily say yes, and this is a fake data because it has been trained on 120 images trained. So this will, at the beginning it will say and this is real and fake, and so when you pass this, isn't it, it will, this label is zero, this is fake, isn't it? So because it has been trained here, isn't it, as I've already shown, it is trained on 128 images, isn't it? 128 images, it can easily, isn't it, it can, it can easily say and this is a real and this is fake. So zero, isn't it, to the generative images at the beginning. So but, isn't it, we give this fake label as one. Why we are giving this fake data as level one? So we should give zero, isn't it? You think, isn't it? But why we are giving this level? So that's the logic, isn't it? That's the trick, isn't it? It's just a trick, isn't it? You can see just trick, isn't it? So we are generating data from the generator and wanted it and just giving the label as one, isn't it? This is actually a fake data, but we are giving label as one. See, isn't it? Directly say, I have been trained on 120 images, I will give this label as zeros, and so it knows what is real and what is fake, isn't it? So it will zeros, isn't it? And if you consider, isn't it, if you consider this whole model, isn't it, whole model from here to here, isn't it? from here to here. If you consider the whole model, if you consider this whole model, so is this composite model. So if you consider this composite model as a composite model, if you consider this composite model as we are giving this level as a real y as one, as in y at means at zero as in. So we are giving this. If you consider this whole model as in whole model, as in, so we are giving level as one and model is generating zero, and there is some loss. So there is some loss. So how can we mitigate that loss? How can we minimize that loss? Not mitigate, but minimize that loss. Minimize. How can we do that? Why can I do? How can I do it? Minimize the loss. So and during, I want to also write another point. This point I will write it as so while training, while training, while training, discriminator is in a discriminator. We will not. We freeze the discriminator weights. So B, the point is, and I want to just write it here is, and so while training discriminator, we will freeze the weight. While training, we will freeze while training generator, not discriminator. While training generator is any, will freeze the weight of discriminator. So then there is some loss. There is some loss, and we have to minimize the loss. But the weight has been freeze here. This weight has been freeze, isn't it? We can't because weight has been freeze. So we want to minimize the loss and make this y hat closer to 1 as in and discriminator is capable as in we have freeze the weight, so we have freeze the weight and discriminator is capable, discriminator has been trained, so we this is and we have to make this y hat as in prediction as one, and we can't make changes here, and this is just, and we have another part trainable part is this generator, this we have two trainable part here, and we have freeze it while training generator. So this part has been freeze, isn't it? This part has been freeze, so has been freeze, and we have to do something here, isn't it? So we have to do something here. So there are weights, isn't it? Weights. So so the discriminator losses and forces the generator weights to update in such a way that in such a way that so it will generate real that convince the discriminator. So we have to make the weight updation here, weight updation here, make the weight updation here, accordingly which generate data look real like fake, and which is convincible for the which can convince the generator that it is real, so to do that, we have to update the weight, update the weight, change the weight, when the weight are in correct positions and correct pass this random vectors, and if we pass this random vectors, and this will if you pass this random vector to the generator, it will it will generate, it will generate data, it will not, it will just create images which look realistic. So we have to make the weight in the right values. So so the actually the discriminator is forcing the generator to become better better at generating images. So and why we does not train the discriminator at once. So why we train the 100 images in first at once one step, so why we don't train the discriminator at once, so why we have trained, so the real logic comes here, so if you train if you train this, isn't it? If you train the discriminator uh, at once is in the weight updation here is in can't be happen isn't it? So because the discriminant learn from scratch. So the discriminator is little bit of capable. It know better. It know little bit of better. Better better, but little. It will know just better, little and better. So better than generator. And so images, about images, feature, attributes, and properties of images and edges, and it knows just basic about what images look like, what fake images look like, and it know if we, and as our life is we understand better. We if I want to give you one example. Uh, suppose as you are math concepts in it, so and you doesn't know it, isn't it? Actually, you doesn't know it. I think, and if teacher is in if teach you in teacher teach, but this example will be relevant or not, but try to understand it. So I think you learn as better from your if it doesn't have a strong basics, and it doesn't have a so much strong basic of images. So if we if it is does not have those any basic of images, basic understanding. If the discriminator is too strong, it will not make the weight updation that good, which it helps the generator to learn data representation from scratch. So as kid learns better with kids, isn't it? So as you know, they learn better with kids, and we learn better with our own age, isn't it? So because our vocab and our examples to convey information is similar, and we understand that, isn't it? Actually, isn't it? So give to our friend to make him understand, isn't it? Is similar, and so in that, as kid learns better with kids. So the if discriminator is kid now, so it will help the generators and to learn basic primitive feature of the data, and basic property of the data, and it will learn from actually capture the whole from basic to advanced data representation. So and it will capture the entire the and if we just train the discriminator and just update the weight of generator here, not able to make the it will not conversation. If we just if discriminator is too smart, isn't he? Too smart, the generator actually the data distributions. We have to learn them step by step. So the gradient update will not happen here. So if the discriminator is too good, the gradient update here will not happen in such a way that the generator will learn. So the gradient update, the weight updation will not happen in that way. So that's the logic is why we don't train at all. And this is a composite model. We'll train this. So let's look at it. So composite models. And these are composite models. So I have just I want to give you again big quick recap of what we have done. Training discriminator, we just backpropagate through the discriminator, and we will take the fake images and real images, and we will train propagate through the generator only, discriminator only. And while training the discriminator will not take while training the generator will not take the real samples, and will just generate fake data and pass to the discriminator, and there is some loss, and we will discriminator and will propagate that loss through the generator, and wait and make weight updation. And another thing, we will train this with the discriminator which know little bit better than generator, not that much too smart. Discriminator help the generator to learn. So we will we will do that as any model as any in this is a composite GAN model. So this is a composite GAN model. So this is the main GAN training. So and this the training which we have done earlier is while we have trained the discriminator on the on the fake sample and real sample above was any. This is not the what we have already done. That's not a real GAN training. Is the real GAN training is this. So for the and you can just remove the above training of the discriminator, but this is the main training is in for maintaining we passing these parameters discriminator model, generator model, GAN model, and dataset, large dimension, and number of epochs and batch size. So after that, this is the batch per epochs, and we have nearly 50,000 divided by 120. This will be something this number, and after that defining the half batch, which is the number of batch divided by 2, which we have 120 divided by 2 will be 64. So and this will run for this many times, and this batch per epochs will run this inner loop will run this many times. So batch per epochs, and in the and what inside this loop what we are actually doing is this method generate real samples will just we are just passing dataset and have batches 64, so it will keep 64 real images and this will be the vectors any with all considering with all elements just one just one denoting this is a real listen. So I'm just training the discriminator. After that the same this generative fake samples will generate from this generator model. Right now we are not, this will come from the generator model, so you have to understand that. So this will come from the generator model, and we're passing this many and it will give 64 images with label. And this y-fake because y-fake will be the one dimensional vector, all elements consisting of 64 elements of label of values in 000 indicating that is false. So and again training the discriminator model on batch. After that the generator training starts. For generator we need Latin points, the random vectors in which is the size of 100 dimensional, and number of batches we will generate 128. So and it will also create the it will also create mm, one dimensional vector of length is of length 120 dimension with all element consisting one. And after that we will gonna go train the this composite model, the GAN model which will train the generators only in it. After that just the printing batch for epochs loss both the discriminator loss on the real data and fake data, and after that printing the GAN loss. And in every 10 epochs is just summarizing the performances using the summarize performance method. And this summarize performance method actually take these many parameters. So as it has epochs and I is epochs right now, and Z model, T model, dataset, Latin dimension, and number of sample we are passing 150. So first of all, we will generate real samples. Just take the samples from the real dataset and evaluate the discriminator model. How our discriminator is classifying the real images and just writing the accuracy for real, and just generating data from the generator. And this generator is trained. So in 10 epochs, it has been trained up. It will train for 10 times. So because we are running this more than 10 times, so not 10 epochs. So this right now this gendered fake samples you have to understand it isn't, we will not, we will just, so what we are doing actually here is generator we are just generating from the trained generator, isn't it? So it is not perfectly trained, but it is it has been trained up to 10 epochs. So This will generate some samples. It will just give some x fix and y fix, and again evaluating the discriminator performance on the real and fake data. And so after that, accuracy for real and accuracy for fake, and just plotting and just saving the plot x fake, and this method will defining it. So it will take this x fix the image and the epoch. After that, we will gonna go save this generator model in tiny box. So it will save in this file path, file name. And after that, we will just this is a save plot. This will take examples, which is xfig and epochs, which we are giving here, and n is equal to 7, and it will just add and divide this images. And so after that, it's just normalizing operation here, and after that it will do some subplotting here. So n comma n I plus 1. After that, setuping axis is equal to false, and I am so example of I. So example of i's. After that, just saving the model. So you can just change the content slash train. So it will save here, save in this directory this model. So save this plot doesn't which consists of the which will give us the this many number of sample fake images, and we are saving in this path and pipe plot dot shape figure. So this will shape it, and pipe plot dot close, just closing it, and it will take some time for training. So our training begins, and after some epochs, and in some epochs, our model has been freezes, and in case of just I run it, and it just crashed the session, so and the session will restart. So after that, we can't able to generate data. So if you have as an high-end GPU, you can just train it. But for me, this showing losses, and this is a loss. So D1 loss, D2 loss, and the GAN loss. And this model is not running and just being freezes. So after that, if you have GPU, and you can then run this code, and it will first of all, there are this some libraries. So keras.model, load model, and just randan from the numpy and matplotlib, you can download it and just use this generate latent point functions, and it will return the latent points. And it will, if you pass this latent point, if you pass this latent point into the G model dot predict, this it will predict the images, and this image we are even normalizing it here. So after that, it will create plot is using this method, and it will create some subplots, and it will just show the examples, and just you can see your here, you can see your plot, and if you have GPUs, it will work, isn't it? But for me, it's not just crashing this session again and again. So this is it.